Greetings, physicists. This video will be about how to analyze graphs of objects whose motion is constantly changing, so constant acceleration. So we'll start with this one. We've got a car. It's moving. We have the graph of its velocity versus time. You can see there are no numbers on the graph. And it says we want to sketch what its acceleration graph would look like. So, first off, let me chop this up and let's look at it. I see three different intervals. I see from the origin to here, and then this would be the second interval, and this is the end of the third interval. So I've made three separate areas. And again, this is a velocity versus time graph. We can see in the first interval, right here, that the velocity is changing. It does not stay constant. It increases, in fact. And it's going from 0 to something higher than 0, so we would call this a positive acceleration, an increase of velocity in the positive direction. When we get to the second interval, we have a velocity that does not change over that interval. If you look at the left point and the right point, those are at the same magnitude. So the velocity at the beginning and at the end and at every point in between is exactly the same value. We don't know what that value is because this graph doesn't actually have numbers on it. Regardless, a flat line on a velocity versus time graph is just a constant velocity. So this car is neither speeding up nor slowing down during the second interval. If we look at the third interval, that is a decreasing velocity. That graph's going downward. And it ends up at the very end at 0 velocity. So this car starts from rest at 0, assuming, well, let's just say that starts at 0. Starts from rest, accelerates over the first interval to some velocity, and then stays at that velocity during that interval, and then during the third interval, it decreases, it decelerates until it gets back to 0, back to rest. So, we can even say, there's even one more thing to be said, which is that during this first interval, you can see that that line increases 4 units in the space vertically, and only goes forward 2 units. So it's a 4/2 slope. If you look at the last interval, that line decreases 4 units, but it does it in 4 units of time. So the first line gains 4 units of velocity in 2 units of time. The last interval loses 4 units of velocity, but it does it in 4 units of time. So the acceleration, or the negative acceleration's magnitude in the last interval is less than, or half of, really, the original acceleration. So it accelerated up to speed faster than it slowed down at the end. That's good to know. And we will use that. So let's make our acceleration versus time graph, and I'll do it like this. We are going to need to go negative on this because our last interval has a negative acceleration. So here's A and T, and we'll do the same time intervals. 1, 2, 3, 4, 5. There are 5 of them. Sorry, there are 5 markings. Okay, and we'll go up 2 and down 1. So we said that our first interval had a positive acceleration. And if you look at it, I'll mark this one in green. If you look at that first line again, that slope does not change. That is a constant acceleration. So when I draw on this graph, I need to make that first interval a constant acceleration. And I'm putting it at magnitude 2, just to make it easier later when we have to go back. I may want to do this one in red, actually, just because it'll be easier to see when I get to the second interval. Okay, so that's my acceleration during the first interval, and notice it only lasts up to that first time point, right? All right, then during the second interval, which is 2 points of time, there is no acceleration. The velocity in that first graph was constant, so the acceleration has to be 0. So that means I am on the x-axis for this point. And if we want to connect them, we can. We just put little dot line right there, a little dashed line from there. There's corners on this velocity graph, which is not realistic, but that's fine. And then the last interval, which is also 2 time units long, is negative in its acceleration, but it's half as much. So if the original interval here is that wide, or that magnitude. It has a magnitude of 2. Then this last interval has to have a magnitude of 1, but it has to have a magnitude of negative 1. But it lasts for twice as much time. And I can connect them using this dotted line there. Okay, so that is my acceleration versus time graph for the same car, for that motion over the same time interval. Good times. All right, let's go try another one. Comparisons, love our comparisons. An elevator is moving downward and slowing down. That's a tricky one. And we have 4 graphs, and only one of them is going to represent the motion of the elevator. All right. Well, we have to indicate, let's see, an elevator moving downward and slowing down as it approaches the ground floor. It's approaching the ground floor. So we have to be approaching 0. So I can right away, just based on those 4 words, I can eliminate 2 of my graphs. Any graph whose velocity... Oh, these are not position graphs. Never mind. Nope, I can't eliminate any of the 4 graphs based on that. If these were position graphs, we could. However, but we can, so I'm going to use these 4 words. Or I'm going to use these 2 words. The elevator is slowing down. So its velocity has to be approaching 0. If you're not getting closer to 0, you are not slowing down. So look at our first graph. This is an elevator that starts at some velocity and ends at some higher velocity. And so that clearly can't be our choice. Then look at graph D. This starts at like a velocity of -1, maybe, if there were numbers on this graph. And then it ends at a velocity like maybe -3. But think about it. If you were going in your car, if you were going west at 1 or east at 1, you're still going 1 mile an hour or meter per second, whatever the unit is. And if you're going 3, whether you're going west or east, you're still going 3. So a negative velocity that gets to a bigger negative velocity is an increase in velocity. That's not a slow down, that's a speed up. So this is a speed up, even though it has looks like a negative acceleration. In this case, because it has a negative acceleration and a negative velocity, they're in the same direction. The acceleration is causing a more negative velocity. So that's a speed up. So when I look at these 2 graphs, based on the fact that the elevator is slowing down, either of those represents a slowing down object, because the velocity at the end of the interval is closer to 0 than the velocity at the beginning of the interval. That's important. You get on a velocity graph. This only works on velocity versus time graphs. As you approach the x-axis, you're approaching 0 velocity. So we need more information then. It's moving downward. There's a key thing that I'm going to have to look at. That's the key to this. Which of these 2 is moving downward? Well, it's going to be the one that has assuming that up is the positive direction and down is the negative direction, it needs to have a negative velocity if it's moving downward. And only one of these has negative velocities, and that would be C. If we look at graph B, all of these velocities, all along that line, are above the x-axis. That's positive. If this is 0, then that's 1 and that's 2, right? But if this is 0 here, then that's -1 and that's -2, etc. So only graph C actually has negative velocities, indicating that it's moving downward. They're getting less negative. They're going towards 0. It has a positive acceleration. but we expect that. We have to be getting closer to 0 in order to stop. So that can be tricky to think about. All right. So I guess one last thing to say is that whenever your velocity and acceleration are in the same direction, which happened in graph A and which happened in graph D, graph A had a positive velocity and a positive acceleration. Graph D had a negative velocity and a negative acceleration. So in both of those graphs, the acceleration and the velocity had the same sign. Those were speed-up graphs. In graph B, we started with a positive velocity but a negative acceleration. And in graph C, we started with a negative velocity with a positive acceleration. Those are slowdowns. So when your velocity and acceleration have opposite sign, you are slowing down. All right, let's move on. All right, we're driving a car, and we got to avoid hitting the child. So let's see here. We hit the brakes and we stop after 1.5 seconds. How far do we travel? Now, this doesn't right off the bat have a graph attached to it. And this whole video is about how to use graphs to solve this stuff. You could solve this without a graph. You could definitely use an acceleration equation and get the right answer. But we're going to show you that this could be fairly easy if you use a graph. So let's try it. Let's try to graph this. And we'll do it with a velocity graph. So let me just set up some axes here. And we'll say, as you drive your car at 15 meters per second. So I'm going to mark up here, 15 meters per second. Assuming like this. You see the ball roll into the street, you hit the brakes, and it takes me 1.5 seconds to come to a stop. So somewhere over here, I'm going to come to a stop, and that will take me 1.5 seconds, assuming that 0 here, the reference point, is when I hit the brakes. And so this is a velocity in meters per second this way, and this is a time in seconds this way. All right. So far, so good. Now I need to graph this. We hit the brakes and come to a stop in 1.5 seconds. So if I start at 15 meters per second here, so let's do this in a different color. This is my initial point. This is my final point here at 1.5 seconds. I will have no more velocity. I will have stopped. They don't tell me in this problem that this is a constant acceleration. But there's no other way to assume this and still solve the problem. If it wasn't constant, then it could be anything. So let's make the assumption this is a constant acceleration. And so I'm just going to connect the lines with a straight line. There we go. So I now have a graph. Now, this is a velocity versus time graph, and they're asking how far do I travel? Well, remember that on a velocity versus time graph, the distance you travel, or the displacement, is the area under the graph. So if I shade this area in, I could use this graph pretty quickly to get the answer. Well, if I'm good with math, I could do it pretty quickly. So area of that triangle is half base times height. So half of 1.5 times 15. Half of 1.5, that's 0.75 or 3/4 times 15. That's 45 over 4, which is 1 and 1 with 1 left over, 0.25. So 11.25. How far does my car travel? My car travels a little over 11 meters. Not too bad. So whether or not that's faster than you plugging this into equation, I mean, you would have to look up your equation list and kind of sift through it. This particular graph was not difficult to draw. So I'll let you as students gauge whether you think it's easier to solve this problem using a graph or whether you think this problem is easier to solve using algebra. Although if you were to encounter a test that said use a graph to solve this problem, you would definitely want to use this kind of method. Okay, let's go forward. Uh-oh. No. I'm not trying to move the picture. Move the page. There we go. Move the picture a little. Here we go. 4. Okay, so another car. This time the pavement is wet, and we're going twice as fast. And we see an obstacle, and we're going to stop. And there's a reaction time. All right, this is the real world. This is a good one. So a reaction time of 0.75 seconds before I can hit the brake. So my car is actually going to keep going at 30 meters per second for those 0.75 seconds before I can hit the brake. And then it tells me what the acceleration is. How far does the car travel? From the instant I notice, so this is including that 0.75 second reaction time. This is very similar to the previous problem. And just like the previous problem, there is an algebraic way to solve it. But this video, we'll go ahead and do a graph. So I'm going to graph this motion. Oh boy, I really can't draw straight lines today, can I? Let's try that again. Not any better. That's okay. They don't give me, let's see, they give me a time interval. They say that, let's just make that 0.75. Okay. In terms of time, and then, from the point where I notice it, which was going to be my 0. And they give me at the top, we'll say this starts at 30, and that this is a velocity in meters per second on top, and this is a time in seconds here. So I know one part of my graph. The start of my graph is going to be me traveling 30 for 0.75 seconds until I'm able to hit the brake. So I'm just going to draw that to right there. Okay, so that's the beginning line on my graph. From there, I have to come to a stop. Now, let's see what that's going to mean. I have to drop 30 meters per second. And I'm doing it at a rate of -6 meters per second. So I lose 6 meters per second. I don't know if I drew my axes large enough, but let's try it. In fact, I may redo my axes just for the sake of the ease of drawing. So let's do this. Let's make 0.75 here, because that means that 1 second's worth of time on this graph is 4 squares. And I'll go back up here and erase that. Okay, so I get to there. So if I go forward 1 second, now I also have to do 30 here, so that's 2, 4, 6, 8, 10. So that 30 is in 10 squares, so each square is worth 3, so 2 squares would be 6. All right, 6, 12, 18, 24. There we go. So essentially, and then I can mark off seconds. Now, this I marked from here to here is 1 second. So really, this new marking here is like a 1.75. But I'm just going to do every second after that, like that. Is that 6 in a row? 2, 3, 4, 5. Yeah. All right. So every 1 second, right? Every 1 second, I lose 6 meters per second. Let's do that. So I'm going from here to here, and I have to drop that much. So I have to go forward 4 squares and down 2. So that's that. And then I go forward another 4 squares and down 2. And as you can see, this pattern is going to make me hit the x-axis right there. So if I connect all this, I get that shape. And just like before, they're asking me how far do I travel before I come to a stop. So I basically need this shaded area, which is a non-symmetrical trapezoid. If you would like to do that, go for it. You can also do it like this, which is how I would, is just split it up into 2 shapes. And that would be an easier method as far as I'm concerned. So that rectangle here has base times height, which is 0.75 times 30, or 3/4 of 30. What is that? 90 over 4 to 21.25. So 21.25 meters for that one. And then this triangle here is half base times height. And the base is, let's look at it, 1, 2, 3, 4, 5 seconds wide. And the height is 30 meters per second tall. I didn't do units down here. That's a bad example. Don't follow my bad example. Well, half of 30 is 15. 5 times 15 is 75. So I'll get a number, a magnitude of 75. And I will get seconds canceling, and I will get meters. So I have 75 meters that I traveled during the triangle section, and I have 21.25 meters, so let's add those together. 21.25 meters together, and that's going to be 96.25 meters. All right, that works. So that's my answer. How far did I travel? I traveled 96.25. And again, you can check this with your algebra, see if you get the same answer. You should, unless I made a mistake, which is possible. But the graph can be easier, I think, once you get used to graphs. I mean, this geometry is certainly probably easier than the algebra. Oh, I'm doing that again. I want this. There we go. Last one. Draw a motion diagram and a velocity versus time graph for a ball that we toss straight up. And we're only going to start the diagrams after it leaves the hand, so while it's in the air, essentially. Okay. Motion diagram. Here's my motion diagram. This is the dots, if you forgot. So it starts low, and when it leaves my hand, it's going fast, so it's going to travel real far. Excuse me. And then it's going to start to slow down, and those dots will get closer together. Remember, these are equal time intervals. So that's on the way up. On the way down, so if I draw the downward right next to it, it should go down and increase its speed until it's going real fast. And in fact, those should be symmetrical for free-falling objects. So that's my motion diagram. And if it's a true motion diagram, I can draw the arrow. So the arrow on the way up, and they're getting smaller, and then those arrows on the way down are increasing. Now let's do a velocity versus time graph. Velocity and time. Well, the ball starts with an upward velocity. Some vertical, and it starts off with a very big upward velocity. So I'm going to start out up here with that upward velocity. And as it goes up, those arrows get smaller and smaller and decrease until it gets to the very top. And at the very top, really, it's not moving. So it's going to cross the x-axis somewhere. And when it gets to the bottom, it should be moving as fast as it was when it went up, but in the negative direction. And it takes an equal time interval to go up as it does to go down. So let's see here. If I'm marking this off to, oh, that's a half, okay. So that's 1, 2, 3.5 to go forward. So half, 1, 2, 3 to go down. And if I'm 1, 2.5 tall, I have to end 1, 2.5 down. So this is going to be my final point right there, because this is all symmetrical. And we know that when we let go of the object, it's only going to be under the influence of gravity, so it will be accelerating at a constant rate. So this should not be a curved line. This should be a straight line all the way through, just like that. And this should also make sense when we start looking at how far the ball traveled. If you look during the first period of motion, the ball traveled this displacement. That, I guess, 2.5 units times 3.5 units divided by 2 is the area of that triangle. But look how far it traveled here. Here is the second area. Second area underneath that curve, like so. That area is also 2.5 by 3.5 divided by 2. But it's underneath, so it's negative. So we have a negative area and a positive area, so that should cancel out, and sure enough, the ball should get right back to my hand at the end. So, good stuff. This is an example of a free fall motion that we can analyze using a velocity versus time graph. So, hopefully this is helpful to you analyzing graphs. Again, very useful skill for physics.